Hello and welcome back to Let's Code Physics. We are continuing to develop our electric potential integrator code. Again, the way this thing works is that you've got some charged substance here on some two-dimensional surface. We are interested in getting the electric potential created by this thing at any point outside of it. So we want to be able to look at any point outside of it. The way that's going to end up looking is as a 3D graph where we've got an x-axis, a y-axis, and then a hill and valley system to represent the potential at any point around this thing. Last time, or two episodes ago, we were successful in creating a 1D graph, or a 2D graph, I guess I should say. It's got two axes. Where we've got the potential energy graphed, the electric potential. It's a different thing than the potential energy. It's the potential energy per unit charge. We've got that graphed versus x for a fixed value of y. And that's interesting, but we saw really quickly that we wanted to be able to vary both. And so what we need to do is we need to set up yet another loop to explore the y values. So currently we've got y set at a fixed value. And so we need to do the same thing for y that we're doing for x now. So we need a y min and a y max. And let's go ahead and set y min to be the same range as y min and y max be the same values as x min and x max. We can play around with those later if we need to, but I don't think we will. Just because, you know, may as well make a nice square picture. And then we'll do the same thing here to calculate, our, oh goodness gracious, control copy, control paste. There we go. I'm losing control of my control key there. We'll do the same thing here to get our y step size for graphing. And again, we're calling this number a graph points because we've also got loops over the source of the potential. We've got the charged material, which has coordinates x prime and y prime inside it, and so we've got number of integration points there. Alrighty, so we're going to do the same thing here. We need to set up another loop. So we need for y equal to y min by dy to y max, and we'll take that end out, put it down here at the very end. Let's scroll up here, highlight up here, control I. Cool. That is, let's see, that's a good start. The next thing that I need to do is I need to start storing my y values as well. So I need to have a y array equal to y array comma y. And then I need to initialize that up here. So where did I initialize my x array? I initialized that up here. Cool. X array equals thingy there. Okay, cool. Now here's the problem is I'm appending my x values in this array here, but now that's being looped over once or a complete set every time I loop over y array. So I'm going to have too many of these. So I suppose the best thing for me to do is to only do this if y equals y min. That needs to be a double equals. If y equals y minimum, then do this thing. That way I only end up with one x array. I don't end up with all the x values and then all the x values and all the x values. That's going to be computationally expensive, and then it's also going to create a problem when I go to graph it down here. Speaking of graphing, in order to graph this thing in 3D, I need to use the surf command. And for that, we tell it we've got an x array, a y array, so those are our two independent variables, and then I need the potential array as the dependent variable. Cool. I don't think I want to use hold on there, because I should only have one. You really don't want two surface graphs at a time, I don't think. Cool. In principle, that is all we need to do, except that now that we're running all over the place, right, now that we're going all over the place in terms of x and y, we're going to run into points that are inside the charged surface. We don't want to do that because we'll end up in our integrand here of dividing by 0. And we don't want to do that. That's not a nice thing to do. And so what we'll do is we'll only integrate if we are outside of the charged surface. So what we'll do is, let's see here. So I want to say if, let's see here, if I want this thing to be outside of it, so I want x to be either less than x prime min, right? That's what I call the boundary for the integration. So that's the boundary for the charged surface. Or I want x to be greater than x prime max. And I want for either y to be less than y prime min, or I want y to be greater than y prime max. So in other words, I'm looking for scenarios in which x is outside of the range and y is outside the range. Actually, do I want that? Actually, no, I don't need to worry about that, because if I make it that restrictive, then I'm only going to be looking for points that are in this corner, in this corner, in this corner, and this corner. I will leave out this block here, this block here, this block here, and this block here. So this actually needs to be an OR in between there. I think that means I can get rid of these parentheses, but I think I'll leave them just to be safe. So now we're going to say if we're outside of the range, so we're going to, let me put a little note here to say this is us checking that field point is outside of charged surface. There we go. And so this is going to go all the way to the end of integration. Actually, it needs to go all the way to the end of adding the potential to the potential array. Oh, no, you know what? That's actually fine, because we can put out, we've got potential equal to 0. It'll just be a flat 0 inside there. So that's actually perfect. We'll do an end there. Let's see. So when I have that end, end, let's see here. Let's do a control I there. All right, there we go. That's better. Now this end definitely lines up. Yes, yeah, see the highlighting, it lines up with my if up there. Okay, so we're only doing this if we're outside of the charged surface, and otherwise we'll just put in a 0 for the potential. So that way when we graph this, we'll have the potential graph, and then for the surface we'll just have a flat 0, because we're not going inside there. We're not measuring the potential inside the charged surface. Let's see here. If y equals y min, then we do this. Yeah, that's fine. Let's see. That should take care of it. So let's start with a simple case of a uniform charge distribution. I need to close my graph from the last video. Y'all remember this one from last week, right? All right, let's run this thing. I'm still going to print my actually, let's display the y values instead. Display y just as a check on that. Let's see. I've got 50 graph points. Let's decrease. Let's just have 10 by 10 for right now, just to make sure that it's working, and then we'll make a finer graph later. Oh, undefined variable y max. Oh, I suppose I actually need to call my y max. There we go. Try that again. Okay, it is chugging along now. We will check out the graph when we get it in just a minute. Undefined operator y array. Oops. I do need to call my y array a y array. Are there any other y's that I'm missing that are currently x's? Y. I've got y array there. Okay. Once again. Oops. Okay, I made a grave error. This potential array is one-dimensional. It needs to be two-dimensional. Okay, right. I forgot about that. Let's see here. So I've got my potential array there. Let's see. Let's define a. This has nothing to do with the physics. This is all about the storage of it. Okay, we're gonna have to do this the hard way, which is to get all of the arrays set up as zeros initially and then change them. It's not the way I'd wanted to do it, but oh well. So let's see here. So I don't want to do that. What I want to do is I want to do for I equal what is it called? In graph points. Yeah, in graph points. X array of I equals let's see, I want to have x equal to x min, y equal to y min. So I want to have this be x, y array of I equal to y. Actually, I want this to be plus 1, don't I? Yeah. So that way, what I can do is then I can have x equals x plus dx, y equals y plus dy. And then I need to do a similar thing for the potential array. I need to have an x, I need to have an I going along the x direction in graph points plus 1, and then I need to have a for j equal to 1 to in graph points plus 1. Potential array of I comma j equals 0. And then I need an end there. All right, that will get that set up as an array of appropriate size. And right, yeah, because that'll get that set up that way. And so then what I need to do is, all right, can't do this anymore. I need potential array of, oh bother, I have to keep track of I and j now. Great. Is equal to potential. I don't have to worry about storing x array and y array anymore. Here we go. Let's see, but what I need to do now is I want j to keep track of the y values. J equals 0 here. So I want j equal to j plus 1. I need I to initialize to 0 here. I need I equal to I plus 1 there. And now my potential array should be of the appropriate size. All right. Now it's chugging along just fine. And did I get a graph? Oh, I did get a graph. Yay. Okay. So what we've got here now is our graph. It's looking lovely. It does not have a whole lot of data points. It's rather rigid looking, right? But we do get a 1 over r behavior as we get farther away, so it's falling away like we would expect it to. So let's do this. Let's increase now our number of graph points. Let's make that 50 by 50, 50 along each side. And let's actually take this thing out to 20, I think, just so that we can get it flatter along the way there. So we've increased this, so we've doubled this, but we've increased this by a factor of 5. And of course now the code will move a little bit more slowly, and I will catch back up with you when it has some results for us. Ooh, that is a much nicer graph, yes. Now it's getting these little cusps in here because those are the corners that we're not going into. So if you look at this as a flat thing, right, so that's rotation killing me. That square in the middle, that's the square that we're not going into because that's where the charged thing lives. But we get, as you go farther away, it looks kind of like what you'd expect for a point charge, right? Like a monopole, right? So it's falling away. We saw more interesting stuff when we had not a monopole but a dipole, and that is our charge going like x primed here. This is the thing that 2 episodes ago we started to look at. We got a couple of cross sections of, and now we can get the full graph of it. This should be very exciting to get to look at. I think it's exciting. if you're watching this video, presumably you think it's exciting. If you wandered onto this video and you don't know much about physics, welcome. Physics is a lot of fun, spelled with a PH. Okay, we get the dipole shape that we would expect. You see how it's got this peak here and then this dip here. That's what we were seeing last time. So that's one reason to call it a dipole, is because it's got these two extremes. They are getting cut off a little bit with this chasm there because of the square we're not allowed to go into. You can see that square again by looking at it from the top. It's pretty cool. So we get what we would expect. It is dropping off faster than the last graph did. So that's that dipole term that we saw before. And you can kind of see how we were getting those cross sections before. Now we get an idea of what the absolute maximum and minimum look like. So yeah, this is really neat. This is cool. Let's do one more. So in the last video, we got this octupole moment, not octupole, quadrupole moment coming out. I'm sorry, octupole is just such a cooler word than quadrupole. Not that quadrupole isn't cool, but octupole just sounds really cool. I guess that reveals my origin story as a Spider-Man fan. So we'll try this one and we'll get that graph out, and I think that'll be it for this video. What I want to do after this one is start working on getting more interesting shapes. So the charge density is all nice and interesting, but we're kind of stuck with this rectangular shape. So I'd like to make a better way for us to get more interesting shapes out of the charged objects, because then let's see, December is approaching. Or holiday time is approaching, more specifically, and so we can do some fun shapes like Christmas trees, stars, things like that, to be a little festive when we close out this series. We've made it to 20. Ooh, and this is what our octupole, our quadrupole term looks like. What you notice is we get two peaks and two. So it being a quadrupole gives you 4 interesting features. So that is really cool looking. We're getting a lot flat out there. Let's actually, one more thing. Let's zoom in a little bit on our data. Let's change this back to -10 to 10 for everything there. And this will be our last graph that we look at for this video. Okay, so here we've got our more refined quadrupole graph. So you see we've got our 2 peaks and our 2 troughs. Looks really cool. What's really neat is this this curvature that you get in between there, right? So you've got this thing coming up toward a peak, this thing going down this way. So you've got contour lines like this that just shoot straight down like that. Very cool stuff. Of course, the middle is flat, like we've been enforcing. Yeah, so this is really cool. This gives you an idea of the kind of cool stuff that we can get. What we will look at next time is making more interesting shapes besides a square or a rectangle, and seeing what type of results we get. So I'm going to work on that, probably develop most of it off camera, and then spend some time implementing it on camera on the next episode. Thank you so much for watching. I will see you next time. Bye-bye.